We're going to start our momentum unit, and we're going to define momentum the following way. When you think of a sports team having a lot of momentum, it means that team is hard to stop. So we're going to say momentum is how hard something is to stop. Okay? Now that's a lot like our definition of inertia. Inertia was a resistance to a change of speed, or how hard it is to change speed. We found out that that was mass. So something with a big mass, like a train, it's very, very hard to change its speed. It's hard to speed it up, it's hard to stop it down. Once it's going, it's going to be hard to change its speed. So we're going to look at a few objects here, okay, and determine whether they have a lot of inertia or a little bit, and the same thing with momentum. Now, a ping pong ball going 20 meters per second is a very low inertia. Inertia mass, ping pong balls have and it has a very low momentum as well. It's really easy to stop a ping pong ball. A train going at 20 meters per second has a huge amount of inertia and a huge amount of momentum. Lots of mass or inertia, and it's very hard to stop them. Now here's where it's going to differ. The train at rest still has a huge amount of inertia. It has a lot of mass. It's still hard to change its speed. It's sitting there, I can't just push it and have it move. It's going to take a lot of energy to get it to change its speed from zero. But it has zero momentum. I don't have to do anything to stop it because it's already stopped. And a bullet at 500 meters per second, a bullet has a very low inertia. Okay, and it has very little mass, but it has maybe a medium momentum because it's going so fast it's going to be hard to stop. So there's two things that go into momentum. Momentum depends on mass and on speed, velocity. And the way we're going to calculate it is P equals mv. Now P is momentum. They couldn't use m because m was already mass, so they picked P for momentum. So our example, we want the momentum of a 0.01 kilogram bullet traveling at 500 meters per second. P just equals V, 0.01 kilograms times 500 meters per second. And I get, when I multiply that out, 5. And momentum does not have a unit of its own. So you just get it by combining the two units here. We get kilograms times meters per second. So the unit's going to be 5 kilograms per second. Now, we have a direction here west. Momentum is a vector, so direction is important. So we're going to say it's west as well. Or we could kind of say P is negative 5 kilograms meters per second. If east is positive, then west is negative. Now, when momentum is important, is this. It makes it very easy to solve some problems. There is no outside unbalanced force. Momentum is conserved. Okay, and just like energy conservation, that means total momentum is constant. So when we're doing problems for energy, we pick a point, maybe the top of the hill, and another point, maybe the bottom of the hill, find the total velocity at both of those points, or sorry, total energy at both of those points is equal. It's going to be the same type of thing, but instead of two positions, we're going to do a before and after. So we're going to draw a before and after. Now, instead of calculating potential energy and kinetic energy, we're going to calculate momentum for all objects and then we're going to do P total before equals P total after. And we're going to find these problems to be fairly straightforward. We got a first example, a 200 kilogram car traveling 30 meters per second. It's a stationary 300 kilogram car. So our before picture, we have a 200 kilogram car with a velocity of 30. We have a stationary 300 kilogram. Now our after picture, we are going to have a 300 kilogram car moving at 25. We want to know what the velocity of 200. So the first thing was to sketch before and after. Second thing is find momentum of every piece. And momentum is easy, we just do M times V. So this one is 200 times 30, which is 6,000. Minus for this one, 300 times 0 is 0. Something stationary has no momentum. Now this one, I can't get an answer for it, but I do know it's going to be 200 times whatever that velocity is. And this one, 300 times 5. That's going to be 75. Then we're going to set the total before equal to the total after. So 6,000 plus 0 is my total before. It's going to equal 200 plus 7,500. Subtract 7,500 from each side, make it negative 1,500 equals 200 V ends up being negative 75. And remember, negative just means to the left. Right, this next problem, I'm using this word completely inelastically, and we'll do this a little bit more detail later, but for now, let's just note that that means that they stick together. So, our before picture, we have a 400 kilogram car, east, 600 kilogram car, going back the other way. Velocity of. I'm going to make this negative 8 because if we're going to the left, on the velocity's vector, I'm going to make it negative going to the left. The momentum's vector, it's going to be negative. Then they stick together. And they're moving together, so I can call it a big mass, just a single object with mass without just kind of together. And I want to know the velocity of these. So, P equals mv for each piece. So 400 times 15 is 6,000. Here is 600 times 8. And over here, I don't know what V is, but let's say it's going to be the mass of 1,000 times whatever that V is. Then I do P total equals P total. So before I have the 6,000 plus negative the 4,800. My after is just 1,000 feet. Negative 1,200 is 1,000 feet. And negative 2 meters per second. So the only tricky part about that one was remembering to make this be negative and knowing when they stick together that I can combine the masses. One last example and a couple definitions. Collisions are pretty much always momentum problems. This is an explosion. Instead of two things coming together, they're flying apart, but it's the same type of problem. The before picture for this one may not be obvious. Right? I'm firing a rifle bullet. The bullet takes off at a velocity of 500. The rifle is actually going to move back the other way, but the before, they're both stationary. Bullet is in the gun. This, for both of them, the velocity is 0. I haven't fired it yet, so the momentum is 0. But then my after picture is like this. A gun, which has a mass of 2. And I don't know its velocity, that's what I'm looking for. Bullet, mass of 0.5. And the velocity of 500 meters per second. So I've already found the momentum before. After, I have the gun has a momentum of 2 feet. And the bullet is going to be 0.05 times 500, which is a momentum of 25. And again, I do my P total equals P total. And I get 0 equals 2 plus 25. If I solve that, I'll get P is negative 12.5. Word up here, recoil. Recoil means it shoots backward. That's what happened with a gun. Bullet gets pushed forward, the gun gets pushed backwards. Two quick little notes. An elastic collision is objects bounce off, bounce apart, with absolutely no sticking. And kinetic energy is conserved. And that really is the definition of elastic, is that the kinetic energy is conserved. In an inelastic collision, there is some sticking. Objects go out. With some sticking. Okay? Some kinetic energy is lost. It's turned into internal energy or heat. And if it's totally elastic, okay, that means the objects stay together. So again, the important word here is that in any inelastic collision, some kinetic energy is lost. They may stick together momentarily and then fly apart, or they may stay stuck together, but it is inelastic if kinetic energy is